Hello, my name is Lucas, and today I'm going to present the couple lateral torsional drill string with uncertainties for the Uncertainties 2020 conference. This article was written by me, Master Daniel Lobo, and Professor Thiago Rito. This presentation starts with a brief introduction of who we are, followed by an explanation of the problem. Next, the models both deterministic and stochastic are explored. In sequence, some results are shown, and finally, concluding remarks are presented. We are part of a research group from the Laboratory of Acoustics and Vibrations within the Federal University of Rio de Janeiro. At the moment, we are part of a project regarding drill string dynamics and calibration in partnership with Brazilian oil company Petrobras. We tackle the problem with different methodologies, ranging from lumped parameter modeling, such as the presented in this work, to complete finite element methods, both with third-party softwares and models of our own development. In addition, our research group is working on modern neural network approach. The drill string is an extremely slender structure that is used in the drilling process. It can be divided in two main parts, the drill pipes and the BHA, or borehole assembly. The former occupies most of the extension of the drill string. The latter is usually stiffer and where most of the drilling equipment is located. At the top there is a rotatory table responsible for applying rotation to the drill string and a hoisting system, which allows to control the force between the bit and the rock, the weight on bit. At the BHA region, there are stabilizers, which are responsible for limiting lateral displacement and enabling higher weights on bits. There are both harmless and harmful vibrations in drill string. Harmful vibrations are often referred by its direction. The critical torsional vibration is the stick slip. It is a consequence of the bit-rock interaction and is characterized by the stagnation of the bit followed by its abrupt release. Lateral vibrations are classified as forward or backward whirls. The former is mainly harmless and is defined by the translation in the same direction as the rotation applied. The latter is a consequence of the drill string's interaction with a nearby surface, causing a rolling motion in the opposite direction of the rotation applied. At last, there is actual vibration called bit bounce. This type of vibration will not be explored in this work. Here, the main hypotheses of the deterministic model are highlighted in accordance with their respective degrees of freedom. The first one is that whereas the drill pipes can be modeled as a torsional pendulum, the BHA is rigid to torsion. Also, the speed applied at the top is considered constant. For the lateral degrees of freedom, the drill pipes are considered rigid due to the actual forces. Hence, all lateral vibrations are limited to the BHA. The impact was considered elastic and fluid coupling was taken into account. The drill pipes are then considered as a torsional spring while the BHA is considered as a rotor limited between stabilizers confined between walls, as illustrated. In this figure, omega is the speed applied and, whereas it is constant, the BHA speed is assumed to be the same as the bits. T-bit is the torque due to the bit-rock interaction and the WOB is the weight on bit. Here, the equations of motion are presented. The equations for lateral vibrations are similar to a Jeffcott rotor in polar coordinates. The equation for torsional vibrations follow a pendulum equation where three torques are highlighted: the bit-rock interaction torque, the torque due to the lateral impact, and the torque due to the constant rotating speed at the top. As aforementioned, an elastic impact force is considered in addition to a smooth friction model. The stochastic model considered a random friction coefficient. The main hypotheses were based on experimental values found in the literature. The mean value was considered to be the deterministic value for the coefficient. The support of the distribution was chosen to englobe those of the literature and other extreme cases, as a frictionless scenario. The final hypothesis is a coefficient of variation of 0.5 that is chosen to guarantee the robustness of the distribution. In sequence, the channel entropy is maximized with the assumed constraints, which led to an truncated normal distribution. The deterministic results regard regimen identification. For that, each type of phenomena is identified separately. To identify the Whirltype, lateral displacement data was rewritten in complex polar coordinates. In sequence, a fast Fourier transform was applied to it, providing real frequencies. If the real frequency of highest amplitude is positive, then it is defined as forward whirl, Otherwise, it is classified as backward whirl. To identify severe torsional vibrations, the amplitude in torsional speed is analyzed. If it is higher than 0.8, then it is considered severe. Finally, to identify the type of contact, the mean radial displacement and the maximum radial displacement were analyzed. If the mean displacement is greater than the clearance, then permanent contact is considered. If the mean displacement is smaller than the clearance, then the maximum displacement is observed. If it is higher than the clearance, then there is impact. If it is smaller, then there is no contact. If we gather all possible combination of phenomena, there are 12 distinct regimens. However, not all of those are expected. For instance, a backward whirl without contact should not be observed. Different drilling configurations were explored with the deterministic model. In each run, the initial conditions were reset and a different combination of weight on beat and rotation at the top was used. In sequence, the phenomena present in the simulations were identified and with it the overall regimen was classified. At the right, there is a map containing regions of distinct regimen. From the 12 regimen, only 5 were present in this set of simulations. The first region is a safe zone, where only harmless forward whirl is present. The second region is defined by severe torsional vibrations and forward whirl. The third region, there is backward whirl with permanent contact. The fourth, a combination of both severe torsional vibration and impact. The fifth and last region is a combination of severe torsional vibrations, backward whirl, and impact. For the stochastic results, the Monte Carlo method was used. Several maps were simulated and the probability of occurrence of each phenomena was calculated. With these maps containing the probability of occurrence of harmful vibrations were generated. The figure at the right presents the convergence of each point of the probabilistic maps, considering the quadratic mean convergence of the radial displacement. The first map analyzed is the backward whirl probability map. The red lines define the regions where the backward whirl was observed in the deterministic regimen map. The black and white color gradient provides the probability of occurrence of the backward whirl. A transition between forward whirl and backward whirl can be observed in the frontier dividing the deterministic regions. In addition, a slight increase in the backward whirl region is observed. The second map analyzed is the impact probability map. Whereas the backward whirl regimen map was slightly affected, the occurrence of impact was greatly changed. While impact was formerly comprised in the regions with severe torsional vibrations, it is now expanded to the region of backward whirl. Near the transition between forward whirl and backward whirl, the impact is more likely to happen, which leads to a backward whirl with impact, which was unobserved in the deterministic analysis. As the weight on beat and rotation applied are increased, the probability of impact is reduced. The third map presents the stick-slip probability map. Even though a coupling between the lateral and torsional degrees of freedom were explored, the effects of a stochastic friction coefficient led to minor impact in torsional vibrations. In summary, a deterministic model was provided and a stochastic model for borehole wall friction was developed. In sequence, maps were generated to evaluate possible regimen in a deterministic approach, where 5 different regions were observed. A similar procedure was then conducted to evaluate the probability of occurrence of critical vibrations. Of the phenomena studied, the occurrence of impact was the most affected by the inclusion of an uncertainty in the friction coefficient. In addition, different regimens were observed when the stochastic model was studied. Finally, I would like to thank you for watching the presentation of coupled lateral torsional drill strings with uncertainties for the Uncertainties 2020 conference. Further discussion will be held on June 29, 2020.